So the valence bond theory is useful in helping to understand why chemical bonds have specific lengths and strengths, as well as why molecules form specific three-dimensional structures. However, it cannot explain certain molecular properties like paramagnetism or averaged bond lengths. The picture below shows the behavior of liquid nitrogen and liquid oxygen in the presence of a magnet. So when liquid nitrogen is poured over a magnet, it just passes through. This means that the molecule nitrogen, or N2, is diamagnetic. However, when we repeat that experiment with liquid oxygen, we can see that the liquid is actually stuck between the magnets, which means that oxygen is paramagnetic and it's attracted to magnetic field. So you may recall that magnetic properties depend on the type of electron pairing in orbitals. When all the electrons are paired, the species is diamagnetic. When there's some unpaired electrons, then the species become paramagnetic. If we look at the Lewis structure for the oxygen molecule, you can have it two ways. You can draw it so that it has single electrons, which will then explain why it's paramagnetic. But if you draw it this way, it violates the octet rule because each oxygen only has 6 electrons, which of course is inconsistent because we know that O2 is a stable molecule. On the right, we draw oxygen in a way that satisfies the octet rule, but in this case, all the electrons are paired, which means that oxygen is diamagnetic. So neither drawing is able to fully explain why oxygen is both a stable molecule that is paramagnetic. Now, another major feature that we have observed in molecules is this existence of average bond lengths. So you recall that we discussed this in a separate video when talking about resonance structures. For example, in ozone, which can be drawn two ways as having either a double and single bond or a single and double bond. Either of these drawings imply that one bond is longer, the single bond, than the other bond, which is the double bond. But when we look at the real structure of ozone, it has two bonds that are the same length. They're both at 128 picometer. Now, the way the Lewis structure solved this problem is by using the concept of resonance, which says that all the Lewis drawings we have are not real, but if we were to average out those drawings, we're going to get the real structure. Now, this is a clever way of getting to the actual structure, but it still means that the model that we have really doesn't predict the existence of this molecule that has intermediate bond lengths. So these two observations is what led to the development of a new quantum mechanical model of chemical bonds. This model is called the molecular orbital model, or just called the MO model. The MO model relies on developing a set of orbitals that are specific to a given molecular species. So these orbitals are different from your standard atomic orbital, whether they are standard or hybrid. They're different than atomic orbitals. So let's take a look at this table, which talks about the difference between the two different models of bonding that we've talked about so far, the valence bond versus the molecular orbital model. So the valence bond model is often called the localized electron model because the valence electrons are shared between two atoms in overlap atomic orbitals. The MO model, on the other hand, is often called a delocalized electron model because the valence electrons from the entire molecule is also spread over the whole molecule in a number of molecular orbitals. So notice the difference here. We're using atomic orbitals, here we're using molecular orbitals. Now, both methods generate the new orbitals using that mathematical operation we call linear combination. However, in the valence bond model, the orbitals that are used come from one atom, whereas in the molecular orbital model, the orbitals that are used come from multiple atoms. Another thing you'll see that's different is the types of the orbitals, the names, as well as the numbers. So you'll see for valence bond, your standard atomic orbital like sp,d,f, and your hybrid orbitals like sp, sp2, sp3. In the molecular orbital, you'll see names like sigma, sigma star, pi, pi star, and so on. The other thing is the type of bonds versus the type of interactions that we would see. So for valence bond model, we say that we form either sigma or pi bonds based on the type of overlap that occurs. In molecular orbital, we don't talk so much about bonds as about how stable the molecule is based on where the electrons are placed, what kind of molecular orbitals contain those electrons. These molecular orbitals may be also called sigma and pi molecular orbitals, as you'll see later, but we don't think of them as bonds. Now, the visual representation of these two models is shown here. The valence bond model is the one on the left, with each of the atom having its own atomic orbital, which overlaps to make the new chemical bond. The molecular orbital is shown on the right. And again, you don't think about bonds anymore, but you think about these molecule having its own set of orbitals. If you compare these two circles here on the left versus this one on the right, that really highlights the main difference of the two approaches. With valence bond, the molecule is made up by individual atoms that are joined together by bonds, whereas in the MO model, the molecule it's a globular entity with its own set of orbitals, no longer disjointed atoms. Now, I want to emphasize the importance of understanding both models. The valence bond model is often the more intuitive one for students, but it can't explain all the molecular features that we observe. So in many cases, the MO model needs to be used in conjunction with the valence bond model to completely explain all the features of a molecule. Now, what we will learn in general chemistry is the type of molecular orbitals you will see for simpler molecules, which are those formed by elements in the first and second period of the periodic table. We will discuss both homonuclear diatomic species, for example H2 or O2, as well as some heteronuclear diatomic species like CO or CN. I'll describe in some detail how molecular orbitals are constructed from atomic orbitals of a simple molecule. We'll use the hydrogen molecule here as an example, and then the ideas that we talked about for hydrogen will then be applied to larger and more complex molecules. So to create the MOs, we will perform linear combination on all the valence atomic orbitals in the molecule. Now, we had discussed the concept of linear combination, so if you need a refresher, make sure you watch the hybrid orbital video. For H2, this means performing linear combination on the two 1s orbitals that each H atom has. Now, I want to point out that in the valence bond model of H2, we don't do any linear combination. The bond in H2 is described as an overlap of the two 1s orbitals. Here in the molecular orbital model, we're going to use those two 1s orbital and we're going to do a linear combination with them to create a new set of molecular orbitals. So even for H2, you can see the difference in how the two theories attempt to model the simple molecule. Now, just like when we constructed hybrid orbitals, linear combination can be thought of as the process of adding waves that are both in phase and out of phase. So these additions are shown here. At the bottom is the probability plot, and then at the top is the corresponding electron density for that orbital. So this diagram shows the addition of atomic orbital wave functions that are in phase, which gives us this molecular orbital wave function. If you remember, wave function on its own doesn't have a physical meaning, but you have to square it in order for it to represent probability. So when we square that molecular orbital wave function, we'll get the shape that's shown here on the top right. This wave function is called sigma 1s. Sigma here has the same meaning as the one we saw for sigma bond, which just means that the electron density is cylindrically symmetric around the bond axis. The bond axis is still the axis connecting the original two nuclei of the hydrogen atoms in this case. The 1s comes about because this molecular orbital is the result of the linear combination of 1s orbitals. Now, if we go ahead and do the addition of the two waves in an out-of-phase fashion, we'll see the result at the bottom for the MO wave function. Just remember that out-of-phase means that the phase is negative compared to the in-phase, which is positive. And then if you square the electron density, you're going to get this shape instead. The MO here is given the symbol sigma 1s star. Now, it's still a sigma molecular orbital because its electron density is still symmetric around the bond axis. So if you rotate that one around the axis to the bottom, you'll see that you get the same positive phase, and then the negative also rotates to negative. So it's still sigma. However, we put the star there because clearly the shape of this is different than the shape of that. Now, just like we used to rank the stabilities of various atomic orbitals, with 2s being being more stable than 2p, and so on, we also want to determine the relative stabilities of these two molecular orbitals, the sigma 1s versus the sigma 1s star. If you look at the sigma 1s, the molecular orbital has electron density that's placed right in the middle of what the two nuclei are located, which of course means that this is stabilizing because it increases the attraction of the two nuclei with the negatively charged electrons that's placed right in the middle of the two of them. So it's bringing them closer. The node, on the other hand, which appears in the sigma 1s star molecular orbital, will mean that the two nuclei are prevented from coming closer because you have no electrons there. So if you have no electrons, there's no reason for the nuclei to be attracted to anything. So just by looking at those shapes, we can tell that the sigma 1s molecular orbital will be more stable or lower in energy compared to the sigma 1s star molecular orbital. Because of these relative stabilities, we also call the sigma 1s MO the bonding molecular orbital, and the sigma 1s star molecule is called the anti-bonding molecular orbital. So to complete the picture, we can draw the energy diagram for these two MOs. A typical diagram is shown right here, where the MOs are drawn in the middle with the atomic orbitals that make up the MOs drawn on the two sides. So the way you interpret a diagram like this is that the sigma 1s and the sigma 1s star MOs are created from the linear combination of two 1s atomic orbitals. The sigma 1s is drawn lower than the sigma 1s star because it's more stable. Now, because H2 has two valence electrons, both electrons will be filled from the lowest energy molecular orbital first, just as we saw in the case of atom. We always start with the lower energy followed by the higher energy. So we draw a pair of electrons, upspin and downspin, in the sigma 1s MO, and nothing in the sigma 1s star MO because we only have two electrons. Keep in mind that all the rules of electron configuration of atoms also apply here, so we must keep Pauli's exclusion principle and Hund's rule in mind. So remember that only two electrons per orbital, and if you have degenerate orbitals, they have to be filled in one at a time. You'll see this applied to molecular orbitals later when we talk about larger molecules. The configuration is written as sigma 1s with parentheses 2, just like you would write 1s2 before. Now you would write sigma 1s2. So now that we know MOs formed by 1s atomic orbitals, we can use them for other molecular species that are also formed by 1s orbitals. And the only other element really that would use this is the helium atom, and so any molecules formed by helium and hydrogen would use the same sigma 1s and sigma 1s star molecular orbitals. So let's take a look at He2, for example. It has 4 valence electrons, so we can draw the valence electron and the energy diagram of the MOs like this, where now you have 2 electrons on the sigma 1s and 2 electrons on the sigma 1s star. The electron configuration would be written this way. Now recall that one of the most important things we learn in electron configuration of atoms is that we can determine what's considered a ground state and what's considered an excited state, right? A state of higher energy, based on where the electrons are located in which orbitals. We can use that similar idea to determine the stability of molecules that are formed given their MO energy diagram. Now the way we're going to do this is we're going to calculate something called the bond order, or BO, of the molecular species. The formula of bond order is shown right here. Remember that what we're trying to figure out is how stable is this molecular species. So what we want is our electrons to be placed in the lower energy orbitals, which in this case is the bonding MOs. And we really don't want any electrons in the higher energy orbital, which is the anti-bonding, because remember the shapes of these is such that this one would cause bonding to happen and this one would interfere with bonding because there's a node right there in the middle. So the formula is representing that concept, which is that we're going to take the difference between the electrons in the bonding and the anti-bonding. Now the larger this number is, the more stable the molecule will be, because then you're going to have more electrons in the bonding versus the anti-bonding. Now we're dividing here by 2 because each bond is made up of 2 electrons. So even though we're looking at the molecule and we're not looking at individual atoms combining to form a bond, we can calculate something that represents bonds in the molecular orbital model. If your BO ends up being equal to 0, then it just means that molecule wouldn't exist. There's no reason for it to exist because the number of electrons are just equally distributed between the bonding and the anti-bonding. However, as we said, the bigger that bond order value is, the stronger the bond. So if you have a bond order of 1, you can think of that as representing a single bond. If you have bond order of 2, you can think of that as representing double bond and so on. If your bond order is 1.5, but that just means your bond is somewhere between a single and double bond. So notice how this is just naturally a solution to the issue of resonance structures that we had to use in explaining these intermediate bond lengths in the Lewis model. Now we don't even have to use resonance. We can just say that that's the bond order given where the electrons are placed in the molecular orbital. So let's apply this bond order formula to both the H2 and the He2 species that we had drawn earlier. So if you calculate for H2, there's 2 electrons in the bonding MO, and then there's 0 in the antibondings. That gives you a bond order of 1. That means H2 has a bond that is equivalent to the strength of a single bond, which of course matches our experimental observation and also matches Lewis theory. Now He2, on the other hand, has 2 in the bonding and 2 in the antibonding, which gives you a bond order of 0. Now this would predict that He2 doesn't really exist or is extremely unstable. Now in fact, when we did an experiment to try to detect the presence of He2, it was really impossible to find until technology was well enough developed to detect it in 1993. Now, due to its low stability, though, this species quickly disappears after the formation, so the best estimate for its bond strength is around 0.01 kilojoules per mole, which is insignificant compared to covalent bonds that are stable, which usually range from the low to high hundreds of kilojoules per mole. So for example, the HH bond strength is 432 kilojoules per mole. So there's a couple more benefits to the MO approach. One of the main one being that because we have electron configuration, we can easily determine whether a species is diamagnetic or paramagnetic. So if we look at H2, we can tell that it's diamagnetic because all its electrons are paired. In addition, if we have odd number of electrons, let's say you have 3 electrons, that's also not going to be an issue because we can just put 2 in one orbital and 1 in the next orbital. These are issues that we would not be able to resolve just using the Lewis structure or the valence bond model. Let's take a look at a few examples on how to draw MO energy diagram for species formed by elements in the first period. Now let's apply the idea of molecular orbitals that we just learned for the first period elements to this question. It says to draw the MO energy diagram for 3 different species and then ask the question of bond length as well as paramagnetism. So because all the species are in the first period, we can just use the first period MO diagram, which is fairly simple. It only has 2 orbitals in it, sigma 1s and sigma 1s star. So you can see that I've drawn all of those diagrams here. And the other thing we need to do, of course, is to figure out how many valence electrons are found in each of the species. So H2 plus would be 2 valence electron minus 1. So the way you do this is the same exact way as you've been doing for Lewis structures calculation for valence electrons. H2 minus will have 3, and He2 plus will have 4 electrons for He2, and then the plus charge would mean minus 1, so it's also 3 total electrons. Now what we do then is place those valence electrons in the molecular orbitals, starting with the lowest energy orbital first. So here we'll have 1 electron, here we'll have 2 electrons there, and then 1 on the antibonding, and then same on the last one. To determine bond length, which is one of the questions that they're asking, we're going to have to calculate the bond order. Remember that you can do that by taking the number of electrons in the bonding orbital. For this one, it's just going to be 1 minus the number in the antibonding, which is 0. So that will give us a bond order of 0.5. The other 2 species, we would take 2 minus 1 divided by 2, giving us 0.5 as well. So actually, when we compare the bond order, all 3 of them have the same bond order, which means that they should have the same bond length or at least close enough to each other. Now, of course, bond order is a very rough approximation of bond length, so I don't want to say that they're going to have exactly the same bond length, but it should be close enough to each other. What about magnetic property? Well, that depends on whether it has unpaired electrons or not. Now, all 3 of them have unpaired electrons in the electron configuration, so that will tell us that all of them would be paramagnetic.